Good morning. Good morning. Today we are talking about energy systems and exercise. Jump right in. Just an overview. Uh, an overview of energy systems we're going to talk about. We're going to talk about the three main energy systems. And I think as a coach, if you want to be in the performance world, you have to have a strong understanding of what's going on within the energy systems when you're providing practical recommendations for a few things, which you'll see. We talk a little bit about fuel utilization. I don't really talk much about oxygen consumption actually at all today. But the last, I'm going to say 5-10 minutes of this is going to be some more practical examples. One more thing to note is that this chapter can seem very biochemistry oriented. Remember, that is not my focus. I'm going to give you guys the simple, important aspects of things you need to know and then move forward. Key points. All right, we got some people here. Got some rather muscular looking men with making crazy faces and a female reading a book. Well, first thing to understand today, the use of your TD. I'm trying to connect this to last chapter. Your total daily energy expenditure. Remember that's energy, your calories, right? If your TD equals 3,000 calories, this is going to be expended using a combination of these three energy systems that we talk about today. And then, most importantly, I think about today is exercise intensity is the key factor determining the primary energy system in the moment. So that's kind of why I put these pictures up where, these people, right, these two guys working out on the left at a crazy exercise intensity are probably utilizing a different energy system. I shouldn't say probably. They're definitely utilizing a different energy system than this woman over here on the right. I hope this doesn't seem sexist at all. It's the first two pictures I found. So let's dive right into just the overview. So as we talked about last week, ATP, adenosine triphosphate, is our primary energy substrate. We need ATP for muscular contractions to take place. When we utilize ATP, right, we are left over with energy, which we use, and adenosine diphosphate and an inorganic phosphate. But we need to get back to ATP, right? Well, how do we get back to ATP so we can actually utilize it for energy? A process called rephosphorylation. So rephosphorylation is an endergonic process of reestablishing chemical phosphate bonds, right? Rephosphorylation is not just ATP or ADP, I should say, right? So I use the example of ADP being converted to ATP, but it could also be used converting creatine to phosphocreatine or creatine phosphate. Okay, so rephosphorylation is that process of reestablishing phosphate bonds, not just with ATP. So how do we do this? We go through rephosphorylation through three energy systems, right? Your PCR system, which I'll talk about in a minute, your anaerobic glycolytic system, and your oxidative energy systems. So there are your three main energy systems. You need to know these. You need to know why they're important. You need to know how long they approximately last. You need to know how fast or slow do they produce ATP. All of those main points are going to be important. Creatine phosphate energy system. So your creatine phosphate or your phosphocreatine or your PCR system, we use those interchangeably, are used to replenish ATP very, very quickly. Super quick, right? And we use creatine phosphate, right, in our muscles to replenish the ATP. So creatine phosphate also has high energy phosphate bonds, and this is located within your muscle tissue. We use creatine phosphate to rephosphorylate ADP and then eventually form ATP. So we now have energy. So what it should look like is creatine phosphate combined with ATP. You add in the enzyme creatine kinase, right? So what does kinase do? It breaks down some of those phosphate bonds, right, in creatine phosphate, and then adds it to form ATP and creatine. So we no longer have creatine phosphate, we now have creatine as a byproduct of this chemical reaction. I also had to put this in here. I generally call it the phosphocreatine or PCR system. I'll probably use PCR a little bit more just because it's shorter, but it can be used interchangeably with PC, PCR, CP, phosphocreatine. I think that's spelled wrong on the bottom. But a lot of different names for the system, used interchangeably. So creatine. Creatine is an interesting substance. As I've already said in other PowerPoints, I talk about creatine a lot in the applied world. Let's jump into what creatine is. So creatine is a substance found primarily in meats and fish. On an average standard diet, it's going to provide about 1 to 2 grams of creatine per day. However, we can also still synthesize creatine in the liver and the kidneys naturally. You can also get creatine through supplements, just like this, micronized creatine. When we supplement or ingest or synthesize creatine, it's stored in our muscle tissue. 1/3 of this is stored as actual creatine. 2/3 is stored as phosphocreatine. And remember, phosphocreatine is what you need, right, to get ATP back, right? Creatine, not so much. So based on this, we should realize that people that have, whether it's vegetarians or anyone that just doesn't eat meat, right, they may have lower creatine levels. So if you do work with vegetarians, you may want to look into recommending some sort of creatine supplement if they're athletes, if they need creatine for explosive movements. Vegans was the word I was looking for, vegetarians or vegans. So after your phosphocreatine, right, or creatine phosphate is used, we're left with creatine, and I showed this on the prior slide. Well, what do we do with creatine? We have to rephosphorylate creatine, actually, to get back to PCR, okay? And this is done through aerobic metabolism in the mitochondria, right? This can take several minutes. So the text denotes that it could take 1 to 2 minutes, right? I've used this guideline from an exercise physiology text in most of my classes, where it takes approximately 5 minutes to return your phosphocreatine levels to 90% of baseline. So what does that mean, right? I would apply this in the gym or in my world of coaching when you're trying to accomplish certain things. So if I'm in the gym and I'm working with an athlete who's working at a very high percentage of their 1RM, right? Let's say 90% of their 1RM, and they're doing it for a triple, 3 reps, right? This is something that's going to take about 5 to 10 seconds, something along those lines. So the triple is going to utilize a lot of their creatine. When they're working at such a high intensity, right, and that creatine is depleted, they need long rest periods. So oftentimes when somebody comes to me and it's only their first month here, they think they only need 1 or 2 minutes of rest between sets. If they do one set of 3 at 90%, I always tell my athletes or whoever I'm working with, you need a minimum of 4, upwards 5, 6, sometimes 7 minutes recovery to get your creatine levels back to baseline so you can perform again at a high level in your subsequent set. So if their focus is power or strength, I tell people to take 5 minutes between sets. Now, I don't tell them it's to get your phosphocreatine levels back to baseline, but I do tell them to take 5 or 6 minutes with the mechanism being this whole phosphocreatine system, right? So there's some sort of theoretical underpinning behind my recommendation. I don't have to tell them, but there should be one, right? Now, conversely, if I'm working with my athletes in track, a lot of people don't understand that, like, if we're doing an all-out 40-meter sprint in practice, a 40-meter sprint might take 4 or 5 seconds, right? If it takes 5 seconds, right, they would think, oh, I could kind of just get on the line a minute later and sprint all out again. It's only 40 meters. It's a 5-second effort. But same exact principle applies, where I'm going to tell them my general rule of thumb when I'm working with my athletes: for every 10 meters of sprint, take a full minute recovery. So if we're taking 5 minutes if we're doing a 50-meter sprint, we're going to take 5 full minutes recovery, even if that sprint only takes 6 or 7 seconds. Okay, so now you guys can start to see how we utilize some of these guidelines in the applied world. So just some final things to wrap up on this PCR system. So one chemical step, very simple, very fast. I already said it's utilized for exercises in that 5 to 10 second range, right? It's an anaerobic process. It does not require oxygen. And then just some examples of some sports. Could be sprinting less than 100 meters, shot put, Olympic weightlifting, jumping, right? These are various things that would utilize your phosphocreatine system. Moving on to the next system, your anaerobic glycolytic energy system. This is the process of breaking down glucose or glycogen without O2 to rephosphorate ADP to ATP. So it's the same thing, right? Our goal is the same exact thing, where we're trying to get ADP to ATP. However, it's a different process, a different chemical pathway. This is used to replenish ATP moderately quickly to quickly. So it's definitely slower than your PCR system, but it's somewhere in between. It's not too slow. This system is primarily active in exercises ranging from 60 to 120 seconds. 60 to 120 seconds. All right, so what is that? That's like a 400-meter sprint in track and field. Most males and females are going to be able to sprint one lap around the track in that 60 to 90 second range. So I did say within the definition where it's breaking down glucose, but it could also be glycogen. Depending on your starting substrate, right? Glucose, right, is going to produce 2 molecules of ATP, and it goes through a process of glycolysis. Glycogen, which is your storage form, right, of glucose, is going to go through glycogenolysis, and it's going to produce 3 ATP. So even though they're still going through glycolysis, right, or some form of breaking down glucose, the ATP produced is actually different, right? And this is important because when we start to look at the Krebs cycle and oxidation, you'll start to see that the amount of ATP produced actually varies a little bit. So just to illustrate, this being a little bit more of a complicated or much more complicated system than your PCR system, right? The PCR was 1 chemical reaction. This is now 18 chemical reactions with 12 different compounds. So one important aspect of this is phosphofructokinase, right, which is the rate-limiting enzyme for glycolysis. Well, what does that mean? The rate-limiting enzyme is the thing that slows everything down. While there are many other enzymes involved in glycolysis, right, phosphofructokinase, right, is the one that's going to dictate how fast or how slow this process is taking place. And this is where I really try to simplify things, where if our starting substrate is glucose or glycogen, we're trying to get glucose and convert it to pyruvate and inevitably convert it to lactate plus 4 ATP and NADH or FAD plus a hydrogen ion. So our reactant is 4 ATP, or part of our reactant is 4 ATP. However, 1 ATP is utilized within steps 1 and 3. This is in Appendix I of your text. So if you want to check this out in Appendix I, and if you want a deeper look at every single chemical step in glycolysis, feel free to take a look. But what you'll see is we actually have to use ATP during glycolysis. And because of that, right, because it costs energy, we don't actually net 4 ATP during glycolysis. Instead, we only net 2 or 3. We net 2 ATP if our starting substrate is glucose. We'll net 3 ATP if our starting substrate is glycogen. So as you'll take note, one of the other reactants is hydrogen ions. So as we are going through this process, we are producing hydrogen ions, which I think I talked about last week. And this is going to lead to a decrease in our pH. And as our blood becomes more acidic, or our muscles become more acidic, what's going to happen is this is going to produce a less than optimal environment for our muscles to contract. And as we have more and more acidity within our muscles, the contractions start to slow down and we produce less force. This is one way to quantify fatigue, right? A decrease in force production. All right, on to our last major energy system. It's the oxidative system, right? So this is your dominant energy system when you're looking at activities that are more than 4 minutes long. So what is that? Running a 5K, swimming a 1K, running a marathon, cycling, anything more than 4 minutes long. This is a much slower energy system, right? So we've now got a hierarchy where our fastest is your PCR, then you've got your glycolytic system, and then you've got your oxidative system. So once again, the PCR system was 1 step. This oxidative system is 124 steps with 30 different compounds. So now you can start to see why it takes so long, right? It's clearly a very complicated process. Now, the oxidative system really has 3 phases, right? It's got aerobic metabolism of carbohydrates, fat, or protein. And then, right, these substrates have to go through, which should be pyruvate, starts to go through the Krebs cycle. And the goal of the Krebs cycle really is to put out ions, right, or electrons that eventually go through electron transport train. So assuming we're skipping the first step, because I've already covered the first step, right? We have pyruvate, which is that end glycolytic substrate. Pyruvate has to enter the mitochondria and must be converted to acetyl coenzyme A. It has to be converted no matter what you're looking at, whether you're starting with protein, whether you're starting with carbohydrates, whether you're starting with fat, right? Pyruvate must be converted to acetyl coenzyme A to go through the Krebs cycle. So oxidation, right? This is the oxidative pathway. Oxidation is the process of giving up electrons, and that's exactly what pyruvate does. It gives up electrons. Reduction is the process of receiving electrons, right? So NAD and FAD both receive electrons, which inevitably go to the electron transport chain. right? So these are your acceptors of electrons. But the most important part of the Krebs cycle, as I already said, is to get these ions, right, to the electron transport chain because that's where most of your ATP is actually produced in the oxidative process, right? So NADH and FADH are shuttled to the electron transport chain, and through a series of chemical reactions, right, they start to produce ATP. Once again, depending on your starting substrate, or depending on the substrate you're looking at, NAD produces about 2.5 ATP, while FAD produces about 1.5. And based on the amount of these compounds that enter the electron transport chain, you can calculate the actual total ATP produced. So the total ATP produced in the electron transport chain is 26 ATP, right? This is 20 from NADH and 6 from FADH. So I'm sorry I'm throwing a lot of numbers at you guys, but I am trying to break it down and make it as simple as possible, which you'll see on the next slide, I think, which is what matters, your ATP total. So through glycolysis, we're producing about 2 ATP. Again, it depends on your starting substrate. The Krebs cycle, 2 ATP. Electron transport chain is about 26 ATP for a total net of 30 ATP. Now this varies. It could be 31, it could be 33. I've seen 38. It really varies. But if you said something between 30 and 38 ATP, that would all be acceptable. Now, here's just an overview of this, right? So you can see we metabolize proteins for energy, although we don't really talk about it very much. We can metabolize carbohydrates, right? Carbohydrates need to be broken down if you have a starch to glue. Oh, that slide. Let's move on. Let's move on. I'm already 22 minutes into this. Let's start to move on to the more practical information here. So normally I would draw this on a board, but what we need to recognize is that your bioenergetic contributions, whether you're looking at your oxidative system or your, let's say, glycolytic system, these things exist on a spectrum. No one system is 100% on or 100% off, 0% working, right? All systems are working at different percentages. At rest, right now, when I'm doing very little, I'm utilizing approximately 85% of my energy to just move my hands and talk to you guys, right? Approximately 85% fat, 15% carbohydrates. Remember, we largely ignore protein utilization for energy. So, well, how do we know this? We can actually calculate this, which is what we talked about last week, through our respiratory exchange ratio. So there's a cool little chart on page 87, which I highly recommend you view because you guys are, if you're in the exercise science program, you're going to use the metabolic cart many times over. And your respiratory exchange ratio really dictates and tells, it tells you what you're utilizing. So when you're breathing into that mask, right, it's measuring how much carbon dioxide you're breathing out, measuring how much oxygen you're breathing in, and through some advanced formulas, it can tell you how much carbs and fat you're utilizing for energy. A score of 0.70 is much more reliant on fat. A score of 1.0 is much more reliant on carbohydrate. You're utilizing more carbohydrate. So I'm going to connect this now to endurance performance. Okay. So we haven't really talked about this just yet, but we do have a fairly unlimited supply of fat for energy. And I mean that. We have an unlimited supply of fat. You could run 10 marathons, or you could go through 10 marathons just solely on the fat reserves in your body. However, our carbohydrate supplies are fairly limited, right? We have enough carbohydrates for approximately 60 minutes of exercise, depending on the intensity. How do we maximize carbohydrate uptake? How do we maximize fat uptake? And can we shift the system of the energy we're trying to use? So just so you guys know, this isn't in your book. If you guys are all confused at where this is coming from, this is just something I like to add. So on the chart on the left, right, on the x-axis, I've got exercise intensity, and on the y-axis, I've got your relative contribution, right? What percentage is contributing for energy, right? So if our exercise intensity is fairly low, let's say 20% VO2 max, which is low, right? Our predominant energy system is, I'm going to say 90% up here. I don't know if you guys could see my mouse, and 10% carbohydrates. As our exercise intensity increases, let's say I kind of just wrote it in here, 50% VO2 max, right? We're utilizing approximately half of our energy from carbs, half from fat. Now, as exercise intensity increases and we get up to 80, 90% VO2 max, we become very reliant on carbohydrates for energy and not so reliant on fat for energy. Okay? And this is kind of what I said before, where 85% of my energy right now while I'm resting is from fat. So the question that has kind of been posed in research and by some endurance athletes is, if we have this near limitless supply of energy, right, of fat, can we utilize more of that for exercise? How do we upregulate that? Okay, and it can be done. So this is a very theoretical depiction, but what you'll see and what you should be able to see is all of a sudden this crossing point of where these start to intersect, and it's 50-50, is at 60% of VO2 max. Again, this is a theoretical depiction of that. However, how do we do that? Well, you can upregulate fat oxidation several ways. You can upregulate fat oxidation by simply going through oxidation more often. What does that mean? Training like an endurance athlete. By training like an endurance athlete, you are going to upregulate fat oxidation. Well, what else can you do? You can exercise in a fasted state. So if you don't eat for a period of 12, 16 hours, 24 hours, there's going to be less blood glucose, there's going to be less muscle glycogen, and you're still trying to exercise, so you still have to get energy, so you're going to utilize more fat for energy, right? So going in a fasted state is definitely going to utilize more fat for energy and shift the system. Another way is through a chronic fat adaptation. So by being in a lower carb state for several days at a time, you can upregulate certain hormones that are going to increase burning fat. Okay? So this seems like a good thing. We want to burn more fat, A, because people like to burn more fat to look better, and B, because it's a limitless supply of energy, right? Well, sorry, some of this is from some other slides. I already said where we've got this limitless supply of energy. This is why we want to utilize fat, right? We want to utilize fat because it's limitless. By utilizing fat, it's a higher energy yield, right? So I already said if we utilize carbs, it's somewhere between 30 and 38 ATP. Well, fat is 130 ATP, right? I'm kind of getting ahead of myself because we're going to talk about fat, I think, in 2 or 3 weeks. But fat's going to give us a lot more ATP. And then additionally, right, carbohydrates store water, right? This is, I think we talk about this next week, but carbohydrates store water. So if you're carb depleted, you're going to store less water and you're going to be lighter, which if you're running a marathon, right, seems to make good sense. You don't want, if you could be 5 pounds lighter, it's less wear and tear on your body. So ignore those. I already told you guys that we've got this limitless supply of energy. this kind of illustrates this, right? Where this is from another text. Our carbohydrate availability is about 60 minutes, upwards of 100 minutes. That's what Juke and Droop states. But fat, like I said, is limitless. 5,000 minutes. It's almost 5,000 minutes. That's many marathons, okay? Well, why don't we all try to be more fat adapted, right, as an endurance athlete? Oh, I'm missing a slide. That's disappointing. Well, the truth is, right, we don't want to be fat adapted because it is a much slower process, right? The number one reason is that it's a much slower process. So while we have this near limitless supply of fat to provide energy, and while it provides more ATP per molecule or per compound, right? The problem is it takes much longer, right? So I already showed you guys it is 124 steps, which just takes simply too long, right? So unfortunately, while in theory it seems to make sense to utilize fat for endurance sports, at the present time, because it takes too long, it doesn't really work, right? It doesn't work in the applied world. So sorry about that missing slide. So last thing I wanted to talk about today was nutrient storage. This is another just more practical example that the text kind of talks about. And kind of what happens when we eat. Well, do we utilize the food right away? Do we, if I eat a 200 grams or 200 calories of carbohydrates, is that going to be used as energy right away? And the answer is obviously no. So at an energy balance, some will be utilized and some will be stored as glycogen. Remember, glycogen is the storage form of glucose, right? Now, it gets stored in your muscle and your liver. Now, once our muscle glycogen specifically is topped off, right, some of the food, a smaller portion of that, is stored as fat, right? Ignore that insulin comment for now. Now, if I'm eating an energy balance or a deficit even, right? So I'm eating under my total daily energy expenditure. A small portion is stored as fat. However, at a surplus, right? At a surplus, a larger portion of those calories end up getting stored as fat. So at a surplus, if my total daily energy expenditure is 3,000 calories and I'm eating at, let's say, 2,500, maybe only 40 calories are stored as fat. But if I'm eating at a surplus and I'm eating 4,000 calories a day, a much larger percentage of the food ends up getting stored as fat, maybe 150 calories. So now, right, because of this surplus, over time, there's this accumulation of fat or adipose tissue. And, over the course of one day or a few days, it's not that much because then all of a sudden, you're getting back into a deficit after 2 or 3 days, say. Not that much fat accumulation. But over the course of week after week, month after month, you look at yourself 2 years later, as you guys, let's say you guys enter the workforce and you stop working out. You look at yourself 2 years later, you say, well, what the hell happened to me? Well, you've been eating at a surplus over the course of 2 years, and maybe it was only a 200 or 300 calorie surplus, but 300 calorie surplus over the course of 2 years is going to lead to accumulation of adipose tissue, and you will retain more fat. Right? That's kind of how that works with nutrient storage when you're ingesting food. I will be giving you guys an article this week that you are to read the entire thing. It is on creatine. So at the start of next week, right, you guys will be quizzed on this article. So make sure you read this Krieger, I forget his name, article. I think it's very, very helpful when trying to understand creatine. For some reason, creatine has a negative connotation to it, which is largely unfounded. Creatine has proven to be very much a safe supplement. So I want you guys to take a look at this article and be prepared for quiz questions at the start of my next YouTube video.